Hello everybody. I am going to be showing you guys some basics of working with Perlin noise. For this demo I'm thinking we will draw a bunch of particles to the screen, something like thousands of them maybe. Each one will be drawn as a point and its velocity or its direction of movement will somehow be affected by the Perlin noise value at its current position. And then we'll draw it in some kind of cool way, maybe have it leave a trail on the screen or something like that. So, got processing open. Just do the basic stuff here. Got the settings function. Not totally sure what all the requirements are for this, but from what I understand, you set up the size on here. So, I don't know, let's do 800 by 500. I think that's it for that one. Then we got the void. You know what? The first one is supposed to be void setup, not settings. It's kind of new. I haven't used too much of this version of processing, so I'm a little unfamiliar with this stuff. But we'll set the background here. It's a nice white. And that function. And then we'll go to our draw function. Just make sure we got everything set up here. I'll draw a basic rectangle somewhere on the screen. And we will run it. What? Oh, I did have it right. Oh boy. There we go. Cool. So we got our white background, our rectangle sketch is working. Cool. So first things first, I will create our class for the particle, and let me just go ahead and save this project. I don't know, Perlin demo. And then go ahead and create a new tab. We'll put our particle class in this. Particle. Alright, we'll go ahead and define that class. Class particle. We know it's going to have a position. Call that P. You know it's going to have a velocity. Call that V. And maybe we'll have an acceleration vector in there. But for now, we'll start with those and see what we think of it. Particle. Define the class. I'm going to set them up in random positions on the screen. So P is equal to new P vector random width, random height. Alright. And then for now, we'll make V just a 0. 0 in both dimensions. Okay, that's particle. Here's a close bracket for the class. I'll create I usually like to do an update and a draw function. So update will update all the values, like its position, its velocity, and stuff like that. And then draw is where I'll actually set up how it's going to be displayed. So for now, let's just say we'll do a small rectangle. Put it at p.x, p.y, make it 10 by 10. Let's get that started and see how it looks. So in this scenario, I think I'll use an array of particles. Alternatively, I would use an array list if the number of particles was going to change. But since it's just I can just use a fixed number of particles for now. It should be fine as an array. So equals new particle. We'll make, I don't know, 1,000 of them. We'll get those initialized and set up. So for int equals 0. For each index in the array, parts I is equal to new particle. Alright, I'll copy that loop. And I will write dot update and parts I dot draw. See if that worked. Cool. So we got 1,000 rectangles. Each one is 10 by 10 random positions on the screen. Okay, so now let's do some updates. So we know we want to use Perlin noise. So for those who don't know what Perlin noise is, it's just a smooth noise function that, at least in processing, supports up to 3 dimensions. And let me just show you guys what that means really quick. Make a new one there. Perlin noise. Go to images. Yeah, so here's a good example. It's just random noise. In this case, it's in 2 dimensions, right? Sometimes you'll see a demo where the 3rd dimension is time or like frame count, and you'll see it kind of shifting through that dimension. But the idea being, we're going to use 2 dimensions here. So the particle's position will be right here, for example. We'll grab the noise value, do something with it to turn it into an x and a y velocity, and then it'll hopefully move through this like some sort of interesting flow field. So float n equals noise. Noise is a function that gets us Perlin noise in processing. We're going to give it p.x and p.y. So p.x and p.y, let me show you one more thing. The difference between this and this is a scale. So if you zoom into this, you're going to get something that looks like that. Just from experience, I know that processing's Perlin noise function, if you just use raw x and y coordinates for the input, it's going to be pretty zoomed out. So it's going to look something like this, sometimes even, maybe not that much, but something like this. So we're going to scale them a little bit. So I'm going to create a scale here. Let's do 0, 1. And I'm going to multiply these by that scale. Like that. Now for the sake of display, I'm actually going to temporarily take these away from the update function, put them into the draw function, and use them to fill these rectangles so you can see how that scale is affecting things. So n is going to be, the return value of noise is always something between 0 and 1. So we'll scale that to 255 so that we can have black to white. So 255 times n. Oops. So that should fill in these rectangles. And you can see, right, like we've got a dark patch here, we've got more of a light patch here, more dark patches here. If I change that scale to 10 times as large, for example, it already looks a lot noisier. That's just making that pattern a little tighter. And if I make it smaller, barely any differences, mostly grays, sort of turning into black here, but not by much. So I found 0.01 is a decent place to start. Oops. So I'll take this back out of here. No need to do this, because the point here is we want to use this to change the x and y velocities. So now we have a value n between 0 and 1. That's the function of our x and y location. We want to use that to create our x and y velocities. So one thing I found that works pretty well is treat that like an angle. So we're going to say float angle, or maybe we'll just use a, equal to n times 2 pi. Alright, so now n is between 0 and 2 pi, or like 0 and 360 degrees. And we can take that and pass it through sine and cosine and create our x and y velocities. So I'm going to say v, our velocity vector, dot set. For x, we'll use cosine of a, and for y, we'll use sine of a. Cool, so now our velocities are set. We're not doing anything with velocity yet. So now that we have our velocity, we are going to add it to our position. So we should be able to p.add v. And that should move our particles along the screen. Sweet. So you can see they're following the Perlin vector field, which is essentially what we've created here. and they end up kind of converging on these lines, which is kind of interesting. We're not updating the background, so it's leaving all their trails behind them. If we want to clean that up, we can put a background call in our draw function that'll clear the screen between each frame. You can see a little more clearly there. Cool. So I don't like these rectangles. I think points would look a lot better. So point doesn't need a width and a height. See how that looks. Okay, they're tiny. And for that reason, I'm actually going to undo this so that they do drag across the screen. Sweet. So that's looking pretty cool. And we can play with the scale here too. Show you what it looks like when it's a little tighter. See, and you can even start seeing some of these repeating patterns because the Perlin noise function is cyclical. And if we change that to a much smaller value, it's going to be big swooping curves. Awesome. Okay, so that's kind of the meat of it. There are some other ways you can convert this velocity. So, for example, I will copy these, comment these out, and I'll make a new version of velocity. So we'll keep scale. Instead of passing in x and y to noise function, I'm going to create two noise values. So copy this. The first one will just pass in the x. The second one will just pass in the y. So again, the noise is based on x and y, but we're kind of misusing, or not misusing, just using noise function in a different way. We'll get rid of the angle, because now we already have two values, and we can just say an x and y. The thing is, we know that this is between 0 and 1. We want it between -1 and 1, because we're using it as velocity. So quick way to do that is you multiply the whole thing times 2. So now it's between 0 and 2. You subtract 1. Now it's between 0 and 1. Sorry, -1 and 1 times 2 minus 1. Alright, let's see how that looks. Let's try reducing our scale. Or I guess increasing our scale. So it's different, it's funky. Whether you call this better or worse, it's kind of depending on your preference. But it's just kind of another way, of using that Perlin noise function. This seems a lot more kind of squarish. So, something different. I think I like the other one more, so I'm going to comment this one back out. And bring this back, and we can mess with it some more. I think I like this scale. So, talking about that third dimension, right? So we can do some stuff with that. So you can pass in time for the third dimension, so millis, which gives you the time in milliseconds since the start of the sketch. Again, this is going to increase very fast, so I usually find I have to multiply this by something quite small. Let's see. So what we should see here is that they do converge on certain paths, but the paths are slowly changing over time. So it's a little more dynamic. I think it'd be cool if the particles kind of like were reintroduced randomly on the screen after they go off screen. So I'm going to do a check for that. If p.x is less than 0, so if it's off the left side of the screen, or p.x is greater than or equal to width, so off the right side of the screen. Same thing with y. p.y is less than 0, or p.y is greater than or equal to height. If any of those are true, we're going to say p.set random width and random height. Now I want to do this before we add the velocity, because the idea is you change the position with the velocity and see where it ended up. And if it ended up off screen, we're going to go ahead and just set it up somewhere else. Cool, so we can see them kind of reappearing as they go off screen. It is kind of going to get really dark black really quickly. So there's a couple ways to handle this. One would be to draw the points at a reduced transparency. So stroke, we'll keep them black. maybe set it up at like 16 out of 255. See, they're barely there, but over time they'll kind of fill in. And I think this is really cool. It gives it a really kind of feathered, organic shape that's, I don't know, in my opinion, a little more intriguing. But hopefully I'm laying the groundwork and you guys can do more interesting things with this. I've experimented with all sorts of funky variations on how we use this A, or essentially this N value, the noise value, pass it through different functions, pass it through the tangent function, I don't know, whatever you want to do. Something cool that I liked was multiplying one of them by a random number between -1 and 1, so it's constantly messing with the x position. And it's cool, yeah, it kind of ends up with this kind of pattern. Almost reminds me of like bubbles coming up through water or something. Yeah, there's lots of variety. Give it a shot. Let me know if you have any questions on how this works. I think it's a pretty simple demo, but it's got a lot of potential. And this idea of drawing particles over time on the screen has served me pretty well. You can come up with some pretty interesting things. So, thanks for watching. Bye.